This is the Fifth Street Bridge street segment that we are analyzing for our project. This is one of the main connection points from one side of campus to the other side. Down in this direction, you have sort of more East Campus, center of campus. And then if you look over on this side of campus, this is where you have Tech Square, the new ISYE building, Scheller College of Business, CODA, and they recently upgraded the street a little bit to include a new bike lane for micro-mobility devices such as bikers and scooters. And so now all of the pedestrians are on the actual sidewalk, and then the bikers and scooters are on the new cycle track bike lane. And so just quick statistics, the street itself is, each lane is about the standard 12 feet, and then the bike lane is, it's two lanes, so one comes in this direction and then one comes in that direction. Each lane is 6 feet, and so that adds up to be about 12 feet. And then it's about a 2 to 3 foot horizontal barrier in between the two. And then on the actual sidewalk, the sidewalk, what's walkable space is like 17 feet. It's really about 20 feet, but because of this like section right here where if you walk, you would run into a light post, like it's not really walkable space. So really, it's actually about 17 feet in reality, but it gets to be very busy during the peak times, peak class transition times in the late morning, early afternoon, and then also in the evening time as well. And so we wanted to study just why this bridge design is so important for the connectivity.
Performance metrics of the Fifth Street Bridge, starting with the PLOS, and we have this big old equation with a bunch of different variables, such as the width of the outside lane, shoulder by bike lane, and the buffer width. And once you plug in all those values that we get a score of 6.57 or an F, and this indicates frequent walking, slower walking speeds, and unavoidable contact with other pedestrians. And we made a few assumptions for this calculation, which included the width of the outside lane to be 12 feet, and as well as the bike lane to be 12 feet, buffer width was 3 feet, and the width of the sidewalk was 17 feet, and then the average speed was 25 miles an hour. For the transit level of service calculation, it was calculated using a multitude of factors such as frequency, hours of operation, and the service coverage. There are two bus routes along the bridge, the Gold and the Cloud routes, so I used an average between them to determine some of the LOS grades when needed. And I determined that not all of these factors are equal, and gave each one what I felt to be an appropriate weight to give the bridge a more accurate LOS grade. So starting with the frequency or the headway, it was one bus every 14.75 minutes for each route. The stops are in service for 22 hours of the day, and there's a stop on each side of this 500-foot bridge. The buses were very cramped and have a high passenger load, and when comparing the data that is on the GT Bus route website to the actual headways, the buses were on schedule only 75% of the time. And once you add them up, based on the weights, get the average, get a score of 4.05, which is just above a B.
All right, then we're also looking at the BLOS, shown from the multiple equations up above. Our AB segment we'll be looking at next slide. For our AB intersection, we assume 0 because we have no data. And for our CFLT, we have 4 along a 1 mile segment along First Street. Next slide. For our AB segment, we have vehicle data that is a combination of both a 15-minute data collection we conducted, as well as estimates created from utilizing TDA data for both the V and PHF values. And then for, of course, street characteristics, a lot of those remain the same, though the PC is a new one, which you can notice from there is quite good condition, likely due to the fact that it's concrete and that lasts longer than asphalt. Overall, this allows us to calculate an AB segment value of 1.842 and a BLOS number 2 value of about 2.0, which places it firmly within a B rating.
Bike level of traffic stress. This metric was measured using the bike level of traffic stress calculation table provided by Northeastern University. The segment of Fifth Street we are analyzing scores a 1 on the level of traffic stress, which is pretty good and is due to multiple factors. Based off of the number of lanes, the bike lane width, and the prevailing speed of the surrounding vehicles. So there's actually a cycle track on Fifth Street, which automatically makes it pretty safe and pretty easy to use. And the surrounding vehicles only travel at about 20 miles per hour with the posted speed limit. And in addition to that, there's only one through lane per direction, with a left turn lane on each end, which, according to the notes, does add 2 feet needed for the actual bike lane width. So, given that the speed is only 20 miles per hour and there's one through lane per direction, it just depended on how wide the actual bike lanes were. They were well over the 6 feet needed if we are including the width of the buffer. So it confidently scores as a level of traffic stress of 1, which means it is a safe and reliable route for all bike users.
For another method to measure the performance of our street segment, we took a survey from a wide variety of individuals who utilize the bridge to determine our utility factors and the probability that people would use it. As shown up here, we have the different kind of responses for utility coefficients and constants and how we weighted them. You'll notice that the weighting of the constants is greater than the coefficients for that reason, because of course you multiply the coefficients. Then you'll see here that our utility coefficients and constants, those are the values we got from the averaging the responses. Followed by this, we then have it where we made an assessment based off of a 1 mile trip from West Campus all the way across the bridge to the end of First Street and for the various t values to multiply by our constants. Now, as shown by, of course, the example equations that we were given in class, the coefficients are, of course, slightly different in our example. We are then able to calculate our VI values as well as our probability percentages. You'll notice that the driving yourself is very high in comparison to everything else, with the second peak being much smaller for biking. Now, this is in contrast to the modes that people normally say they take, which say they mostly walk, followed by a bit of driving, and of course decreasing from there, which implies that there are some changes that need to be made, or at least should be made to the street to better reflect this.
Okay, on to proposed solutions. Driving, particularly, has hidden costs, even though it is people's preferred method of transportation. And so more people end up walking versus driving, which, while that's better for the environment, that negatively impacts our PLS score. So what is our solution to this? Transportation demand management. What we want to do here is really encourage people to adopt strategies that increase the number of people using micromobility, using public transportation, etc. So, information campaign on starter bikes, that's a program that Georgia Tech offers. We want more people biking. We want more people using the Stinger routes, and we want more people using skateboards, scooters, things like that, and using that existing bike lane that's on the street segment, getting off of the sidewalk, improving that PLS score, and making the sidewalk less crowded.